All right, so welcome everybody to the sixth talk of our BD-RIS webinar series, which is organized by the Special Interest Group on Beyond Diagonal Reconfigurable Intelligent Surfaces, which was established in the IEEE Communication Society. Today is my great pleasure to introduce you our distinguished speaker, Professor Swindlehurst, from University of California, Irvine. So Professor Swindlehurst is very well known in the community of wireless communications. Let me introduce his background very briefly before to give him the floor. Professor Swindlehurst received his bachelor degree and master degree in electrical engineering from Brigham Young University and a PhD degree in electrical engineering from Stanford University. He was with the Department of Electrical and Computer Engineering of BYU for 17 years, during which he also held joint appointment as a visiting scholar at Uppsala University and Royal Institute of Technology in Sweden. In 2006 and 2007, he was on leave working as Vice President of Research for Arraycom LLC in San Jose. And since 2007, he has been with the Electrical Engineering and Computer Science Department at the University of California, Irvine, where he's currently a distinguished professor and holds the Nicholas G. and Sue Curtis Alexopoulos Presidential Chair. During the period 2014-2017, he was also a Hans Fischer Senior Fellow in the Institute for Advanced Studies at the Technical University of Munich. And in 2016, he was elected as a foreign member of the Royal Swedish Academy of Engineering Sciences. His research focuses on array signal processing for radar, wireless communications, and biomedical applications. Dr. Swindlehurst is a fellow of the IEEE and was the inaugural editor-in-chief of the IEEE Journal of Selected Topics in Signal Processing. He received multiple prizes, among them the Baker Prize Paper Award, the 2006 IEEE Communication Society Stephen O. Rice Prize in the field of communication theory, and multiple Best Paper Awards by the IEEE Signal Processing Society. Including the Donald Fink Overview Paper Award, a Best Paper Award at the 2020 IEEE International Conference on Communication, and 2022 Claude Shannon Harry Nyquist Technical Achievement Award for the IEEE Signal Processing Society. So before starting, let me briefly remind the rules of this webinar. So the talk will be approximately 50 minutes long, during which the audience will be muted. If you have any questions, you can type them in the chat, because at the end there will be a 10-minute Q&A session in which I will select questions from the chat, or you can raise your hand and you can directly ask your questions. So enjoy the talk, and Professor Swindlehurst, the floor is yours.
Okay, hey, thanks Matteo and Bruno also for the opportunity to give this talk, and also for changing the time so that I didn't have to do it at 4 in the morning, which is good for me and good for you too. So let's see, I want to do this. And then I want to do this. All right. So today I'm going to talk about, I guess, a unique application of these beyond diagonal surfaces that have been the subject of the webinar over the last few weeks, which I've watched and been very interesting. Here's a picture of what it looks like at UC Irvine pretty much every day, today included. So hopefully you can come and visit us sometime. I'd like to first acknowledge that much of this work is the result of efforts by my PhD student, Haoyu Wang, and also my postdoc, Jackie Xu. And then I'd also like to acknowledge some collaborators that have worked on this and related projects. Juhan at Houston, Joseph Nosek, who has helped us with some of the modeling and has been a longtime collaborator in Munich. And then my colleagues here, Ender and Filippo at UC Irvine. And then also, of course, acknowledge my sponsor, which has been the US National Science Foundation. So if you are at this seminar or watching it later, you already know about Reconfigurable Intelligent Surfaces, or RIS, and I'm sure you agree that it would seem that these surfaces will solve all of the world's wireless problems. That's why we're working on them. Coverage enhancement, beamforming gains, interference mitigation, energy efficiency, and so forth. We view them as being important elements of future wireless systems. At least we hope they will be. And if not, it's been fun studying them anyway in the meantime. So let me just begin with a quick look at the idealized model that most people assume, I think, when they work on these surfaces. Some of these assumptions, of course, are subject to some idealized assumptions. So we might have a base station, we have a surface that's controlled by the base station, we have terminals that are communicating with the base station, either directly through a direct channel or through a link that includes the surface. Most of the time, we assume that the impact of the surface can be described by this diagonal matrix of phase shifts and gains. Most of the time, the gains are assumed to be 1, when in fact, they may or may not be. And here's just the standard model. Without the surface, there's the direct channel, if it's present at all. And with the surface, there's not only the direct channel, but there's this induced multipath channel through the surface that includes the impact of these phase shifts on the propagation. And of course, we all know that the benefit of the surface is that it provides these extra degrees of freedom, n, where n is the number of elements in the surface. The surface provides these n degrees of freedom that allow us to modify the channel and perhaps give it some desirable, or as we'll see today, maybe some undesirable properties. So these are the idealized assumptions that are made by most researchers on this topic. But of course, I'm sure most of you are aware that there are some not so ideal considerations underlying the very idealized model that we often use in this research. And these non-idealities, in effect, reduce the available degrees of freedom we have in general. Not so much, but they can definitely have an effect. The phase isn't necessarily tunable between minus pi and pi. The dependency and frequency is quite strong. The gain and phase response of the surface, as we've learned, is dependent on the incident and reflected angles as well of waves that interact with the surface. There's mutual coupling that's often ignored. We're familiar with the multiplicative fading effect, which indicates that we might need to have very large surfaces for them to have an impact in practice. There's extra overhead for channel estimation. Once you estimate the channel, assuming you can, to optimize the performance of the network with respect to the phase response of the surface, it's quite complicated. There's overhead that's required to communicate and configure the surface, and so on. And so accounting for these effects in a realistic way is challenging. And but on the other hand, for someone who wants to use a surface for malicious rather than beneficial purposes, some of these non-idealities aren't too important. And we'll see that, in fact, it's helpful. So today I'm going to talk about adversarial reconfigurable surfaces that would, instead of creating a favorable propagation environment, surfaces that under the control of a malicious entity could in fact initiate a physical layer attack on the communications. So one such attack that you can immediately think of is what I would refer to as a channel cancellation attack. And in a channel cancellation attack, the idea is to take the reflected signal through the surface and try and cancel the desired direct path signal such that the SINR at the receiver is quite low. And so obviously the opposite application would be to try and enhance the signal to noise ratio. You could also use the RIS to do exactly the opposite, and that's degrade the quality of the channel. This is, well, in principle, this is possible. In practice, it's likely not easy to do because it would require that the attacker have full channel state information for not only the reflected path through the surface, but also the direct path to the users, which may or may not, which will most likely not available. And not only that, it would require fairly accurate and modeling of the surface's behavior in order to exactly null out this direct path signal. So while in principle this kind of attack could occur, in practice it's quite difficult to actually implement it with success. The kind of attack that I want to talk about today is what I refer to as a channel reciprocity attack, or crack for short. And in a channel reciprocity attack, basically what we do is we make the uplink channel that includes the direct path and also the reflected path through the surface. We try and make the uplink channel different from the downlink channel. And we'll talk about two approaches today. One that we refer to as disco, and the other that is I'll focus on more, which is related to the use of surfaces that are non-reciprocal. And this is where we'll tie in with the beyond diagonal RIS idea. So let's talk a little bit about what a crack is, what a channel reciprocity attack is. You probably are aware that time division duplex systems, they rely on channel reciprocity, or at least the assumption of channel reciprocity, or at least a channel that has been calibrated to be reciprocal. The base station uses uplink pylons to estimate the channel, and then the base station designs for example, a downlink precoder W, assuming that the downlink channel is essentially just the transpose of the uplink channel, perhaps after some calibration and other things. So on the downlink, we have the signals that are being transmitted. We have the precoder. It goes to the downlink channel, assuming the downlink channel is in fact the transpose of the uplink channel. The precoder then interacts with that channel, and the precoder is typically designed to essentially unmix the effect of that channel so that we get a series of parallel channels that allow the individual users to decode the messages that are being sent. So that's the ideal situation. The idea behind a channel reciprocity attack is very simple. We just try and make the downlink channel different from the uplink channel. And that then, if the base station is unaware of what's going on, that means the precoder will not, in fact, diagonalize the channel, and unanticipated multi-user interference will be introduced into the network, degrading its performance. So as I mentioned, we'll talk about two types. The first one, the disco crack approach first, and then second, the attack that's based on the assumption of a non-diagonal surface. So as the name implies, the disco crack approach basically envisions the surface as acting like a disco ball. And I'm old enough, probably I'm one of the few old enough in this group to remember what a disco ball was like back in the era of disco dancing. You shine a light on a disco ball and it reflects the signal in random directions, and it's quite fun and exciting. It makes for an enjoyable dance experience. But here, it could be used to disrupt a wireless communication system. The simplest approach, again, is very simple. what you would do is during the uplink training, you would set the surface to one state, say phi 1, and then during the downlink transmission, you would set the surface to another state, phi 2. And as long as you chose those two states to be non-symmetric or non-equal, then the uplink and downlink channels will not be reciprocal. Even if you calibrated the uplink channel and downlink channel at your local transceiver, the RIS itself would ensure that the surface is not reciprocal overall between the two phases. And so if the two channels are not reciprocal, the uplink and downlink channels, multi-user interference will be introduced. And this type of attack doesn't require any channel state information, just make the two states different. You can't overcome this attack by increasing the transmit power, because that just enhances both. It enhances the non-reciprocal effect. It can't be overcome by increasing the number of antennas at the base station. And this attack can be launched without really any precise modeling for the surface. There's no need for robustness here. You just create two different states for the surface, and the non-reciprocity is achieved. But it does require some degree of synchronization with the legitimate system. You have to know when the uplink and downlink portions of the communication occur. One way around that is to just use what you might refer to as a persistent disco. And it's the same as the simple disco attack, except just that the surface just keeps changing randomly. There's no synchronization. It just is always changing all the time, both during the uplink and during the downlink. So it kind of just creates a completely non-stationary, fast-fading channel that really makes it difficult to implement a TDD scenario. Now here, though, if you employ some kind of random phase shifts at the surface, even though the channel won't be reciprocal instantaneously, the statistics, on the other hand, could be very easily reciprocal. So channels are not instantaneously reciprocal, but statistically they are. And for example, this can be exploited. The covariance matrix of these perturbation terms are equal. And for example, one could estimate the strength of this varying channel in time using uplink data or user feedback, and then employ a minimum mean squared error precoder for the downlink. And it's been shown recently in some work together with Juan, Juhan, and others, that in fact, the presence of the adversarial surface in this kind of approach can actually enhance the performance of the link rather than degrade it. And so there are some drawbacks to using this persistently random approach to trying to change the reciprocity of a channel. All right, so this is a technique that we've been working on together with, as I said, Zhu and Juan and some others. And today I want to talk a little bit about something different. We want to try and maybe improve channel reciprocity attacks. What do we want? Well, we want methods that don't require channel state information, that work that allow an effective attack no matter how large the base station array is, no matter how much power the base station can transmit. It doesn't require the need for a precise RIS model. In other words, the attack can be effective even if we can't model all these non-idealities that I talked about. There's no need for synchronization. You can't exploit channel statistics to try and enhance the performance. And so how are we going to get it? Well, we're going to get it by using these non-reciprocal RIS that I've hinted at so far. So here's a picture that you've probably seen before and is taken from one of Bruno's papers. This is a picture that depicts what I would call a standard diagonal RIS with 4 elements. Each of the elements is these antennas are basically antennas connected to and terminated with a tunable impedance. Here's a picture of a lumped circuit element model for one such element. And you can see it's basically like a little antenna with a tunable. In this case, this is a model based on a varactor diode. So the properties of the varactor diode, more specifically its capacitance, can be changed by means of a biasing voltage. And as that voltage is changed, you adjust the impedance that's seen looking into that terminated antenna port. And associated with that impedance will be a particular reflection coefficient that determines what happens to an impinging energy wave that hits that element, how much will be reflected, how much will be absorbed, and so forth. So we have an incident wave xi, say, impinging on this little RIS element. We have a reflected wave. This phi matrix is what determines what's reflected based on what impinges on the array. And we can go through a simple analysis, in this case, a 4-port analysis of the surface with impedances that we tune, Z tilde. We could define the impedance matrix associated with this little network. And in this case, it turns out to be a diagonal matrix because none of these elements are connected to each other. In this case, we're assuming there's no mutual coupling for simplicity. So the impedance matrix will be simply a diagonal matrix that contains these impedances. If you compute now phi, which is essentially the scattering matrix of this 4-port network, you will end up, since Z is diagonal, you'll end up with a diagonal phi, like we always assume. The elements of the diagonal will be equal to 1 if these impedances are purely reactive. Otherwise, they'll have a gain that's maybe slightly less than 1 because of some loss. So this is why we end up with the standard idealized model that I mentioned earlier, with a diagonal scattering matrix. But a more general approach is possible with interconnections between the elements in this surface, as was pointed out, of course, and that's really the reason why we're here, is because we're interested in the generality provided by this beyond diagonal surface. Here, of course, we will have, in general, we could potentially have 16 different impedances that connect the 4 different elements together. We could calculate the impedance matrix in the same way that I mentioned before. It's a little more complicated now to get a nice form for this matrix, but you could calculate it. You could also calculate the scattering matrix phi in this case, and because now the impedance matrix will be a full matrix, the scattering matrix phi will be a non-diagonal matrix. And that's why, of course, we get the name beyond diagonal RIS. Now, however, it will still be symmetric. It will still be a symmetric matrix, but not diagonal. And the properties that I mentioned before will hold in a generalized sense as long as the elements of these as long as the impedance of these interconnecting elements are reactive, then this scattering matrix will be a unitary matrix. Otherwise, if there's some loss, then this relationship will hold. All right, so this is not new to this group, so I'll go on. So as I mentioned, because the scattering matrix here is still symmetric, this impedance network will be reciprocal, and this particular surface will still be a reciprocal surface in the sense that the uplink and downlink channels that go through this surface will be just transposes of one another. Some of the, I guess probably the earliest work, or among the earliest work that considered surfaces that were beyond diagonal, at that point they were referred to as non-diagonal surfaces in this original paper that was in 2022. This work suggested that indeed the phi matrix would be would not be symmetric, or could potentially not be symmetric. And in fact, you could achieve ideally a scattering matrix that is, in effect, a permutation matrix. Energy entering one port or one element of the network would be completely reflected through another port, perhaps with a phase shift change. And so in that case, you might end up with a phi matrix that looks like a permutation matrix, but instead of ones in every location, you have tunable phase shifts that are governed by how you would design this particular network. It's not clear that you can actually do this in general, in other words, with an arbitrary permutation, as shown here, if you use a physically consistent model. And I want to talk a little bit about that today. So, I mean, I'm not saying it's impossible, but it's not clear to me how you would implement an arbitrary permutation matrix with such a configuration. But we'll show that under certain circumstances, you can actually achieve a constrained permutation matrix. But for us, the important point will be that you can obtain a phi matrix that will be non-symmetric and hence will generate a non-reciprocal channel. So how would you create a non-reciprocal surface for which the scattering matrix is non-symmetric? Well, if you're using reciprocal devices like tunable impedances and antennas that are, in theory, reciprocal, you can't do it. So you'd have to add some kind of non-reciprocal device to the surface to make it perform in this way. For example, an isolator, or more generally, a circulator could be used. These are non-reciprocal microwave devices, very well known, mostly used for isolating simultaneous uplink and downlink transmissions from, for example, a full duplex situation. But in theory, at least, you could take a reciprocal device and make it non-reciprocal by judiciously adding these non-reciprocal devices inside. So let's look at an example. And let's look at, let's just start out with a simple two-port model for a single RIS element, a non-terminated. So this is an RIS element that hasn't been terminated. And so energy can come and go from both sides. In this case, we'll assume that in addition to the standard tunable impedance that you might have with a varactor diode, there's another one. So we have two potential knobs to turn and adjust the behavior of this element. In this simple case here, you can calculate the impedance matrix of this two-port. Very simple to do so. You can calculate the phi matrix, the scattering matrix for this two-port. And you see you get but it is symmetric. It's still a symmetric. I hope you can hear me. My computer's telling me that my connection's unstable. Hopefully you can still hear me.
Yeah, just for 1 second. I couldn't hear.
Okay.
Oh, yes.
All right, so let's take this two-port RIS element and let's connect three of them to a circulator. So a circulator is a three-port network. And we're going to connect one RIS element to one port of the circulator, the second one to the other, and the third to the final or the other port of the circulator. Right now, we'll let the scattering matrices for the individual RIS elements be arbitrary, but they will be symmetric because each element here, as depicted, is a reciprocal device. But hooked together with this circulator, they would become non-reciprocal. And the scattering matrix for a standard circulator, ideally, is this permutation matrix that we were talking about before. Non-symmetric, obviously. So the idea behind a circulator basically is that information that flows from one direction is fed to another direction, but not in reverse. Information that flows, or information I should say, or energy that flows from this element is not funneled back to the source here, but funneled in this direction. and energy from this that's reflected or retained by this element flows back to the first element. That's why they call it a circulator, because the flow of energy occurs in a circle rather than back and forth between elements, as you would normally expect with reflections and incident energy going in both directions. And this is what generates the non-reciprocity of the network. So if you wanted to draw a simple picture of what's going on inside the circulator, this is how you could basically describe it. You can see that outgoing energy here is fed only into this element. Outgoing energy here is only fed into this element. And then the circle is completed by this flow here. And by adjusting the impedances, the scattering matrix of each of these elements, you can obtain an overall 3-port network for this little configuration that has this representation here in terms of the scattering matrix elements of each of the individual RIS elements. And you can see that this matrix is non-symmetric. In fact, these terms D1, D2, D3, which essentially relate the signal path in this direction for each element, or the strength of that path, D1, D2, and D3 are the terms that are mainly responsible for this asymmetry. You can, by proper choice of the scattering elements of these matrices, or of each individual RIS element, you could make the diagonal elements of this scattering matrix 0. In other words, energy that enters from outside the system at one RIS element will be fed through and reflected by other elements, not by itself. However, there's no way with this configuration, in other words, for arbitrary scattering matrices for each of these elements, there's no way to use a group-connected architecture here with 3 RIS elements through a circulator. There's no way to get it to, there's no way you could achieve this permutation matrix structure here that I'm showing, which was the assumption in that original work I was talking about in 2022. So this particular architecture, at least, could not achieve an arbitrary permutation matrix like the one I've depicted here. So let's go to a simpler case. Let's take the circulator and basically turn it into an isolator by terminating one of its ports with a tunable impedance. So we still have 2 RIS elements here, with each with 2 tunable impedances themselves. But instead of having a 3rd RIS element, we just terminate it with another tunable impedance. So this is just a group-connected RIS with a group of 2. And the circulator here is serving as an isolator. In other words, energy flows in one direction here and only backwards through this tunable impedance. That's the reason for the non-reciprocity. A very simple circuit. It turns out you can show that with a proper choice of these 5 impedances, you can in fact achieve a matrix that has this, I would say, this anti-symmetric structure. And the phases of these anti-symmetric terms, theta 1 and theta 2, it turns out can be arbitrarily chosen. So at least in the 2x2 case, you can achieve an arbitrary permutation with a completely arbitrary tunable phase. Again, this is assuming the ideal case where there's no loss. We could hook up 2 of these together and create 2 or more of these together to create a larger surface. And so we could obtain a larger phi matrix, a larger scattering matrix that itself is a permutation matrix, but the permutation is constrained in the sense that it has to occur with pairwise connections. So in other words, we could, for example, if we grouped elements 1 and 3 together and elements 2 and 4 together with this isolator, we could obtain a scattering matrix that looks like this. So it's not an arbitrary it's still a permutation matrix, but it has constraints that the off-diagonal elements are paired up because of this two-element isolator structure. So why would we want to do this? Why would we want to do? Well, first of all, again, the idea is to implement a channel reciprocity attack. Well, what's the advantage here? Well, the advantage here is that this particular type of approach of generating non-reciprocity inherits all the benefits that we had in the DISCO system. No CSI is required. I mean, you could plop one of these down with an arbitrary configuration. It's going to disrupt the reciprocity of any wireless channel that interacts with that surface. Doesn't require any active transmissions. You're not actively jamming the channel. The surface is just creating inherently multi-user interference. You don't have to be synchronized. There's no synchronization. You just, in effect, the surface is basically a fixed surface. It doesn't change. It doesn't have to change. You can't thwart this non-reciprocity by increasing the transmit power, the number of antennas at the base station. There are no channel statistics to exploit here. You're not changing the surface in any way. You don't have to have a precise model for the RIS behavior, just as long as you've created this non-reciprocity somehow. But in fact, if you do have some partial CSI, and you can do some modeling, if you are willing to try and model the behavior of these surfaces, you can optimize the performance to, in fact, enhance the effectiveness of the attack, as I'll show you in a minute. So here's, I just want to show you a few examples, and then I'll end with maybe some other more positive uses for a non-reciprocal surface at the end. But here's an example of the performance you could achieve. So here we have a 128 element base station. We have 32 RIS elements, so we only have 32 knobs to play with. And for this first pair of plots, what I'm going to show you is the case where this is the performance you could get if you assumed you could arbitrarily permute this scattering matrix. So this would correspond to the original assumption that was made in that earlier 2022 paper, which maybe is an idealized assumption in some sense. So, and let's assume the base station is just doing maximum ratio transmission for its precoder. The orange line on this histogram shows what the sum ergodic rate would be for a system with, and I've forgotten to put down how many users there are. I think there are maybe 8 users in this example. And so you can see that with maximum ratio transmission, MRT, the sum ergodic rate is somewhere between 200 and 225 megabits per second per hertz, or megabits per second. This is assuming a fixed bandwidth. Whereas if you place this non-diagonal surface in the vicinity of the base station, you can see that the sum ergodic rate is reduced. The dark blue histogram here corresponds to the case with a Rayleigh fading channel, with Rayleigh fading channels. And the light blue corresponds to the case with Ricine channels. And so you can see that with a Ricine channel, you sometimes get far worse performance and sometimes even better performance, depending on, it's very sensitive to what the line of sight component is relative to the random configuration of the surface. But already you can see there is a fairly good degradation in rate that's achieved by this, or the presence of this non-diagonal surface. And the effect is even more pronounced for a zero forcing precoder. You know, zero forcing precoders trying to eliminate multi-user interference. The non-diagonal surface is preventing that elimination by interjecting multi-user interference. And so instead of a sum ergodic rate of 1,000, which would be achieved without the presence of the surface, the sum ergodic rate is reduced by almost a factor of 5 or more, below 200. depending on whether the channel is Rician or Rayleigh. Again, so this is for the case where you might be able to have an arbitrary phi matrix. If you constrain yourself to this physically consistent pairwise permutation that I just talked about, with these isolators in randomly paired, for randomly paired RIS elements. And in this case, we're actually going to do something even simpler. We're going to set the phase of these two elements to be theta 1 and theta 1 plus pi, in a sense to try and create the biggest the biggest asymmetry as possible, as big an asymmetry as possible. Where theta 1 is random and where the choice of the connection pairs is also random. And what we see is you get essentially the same or actually even better performance in terms of a reduction in the sum ergodic rate compared to the case where you could arbitrarily change phi into an arbitrary permutation matrix with random thetas. And so the physically consistent modeling here doesn't really hurt us in the sense that it doesn't constrain the impact of the attack. In fact, in this case, because the reason this happens is because we're able in this case to enhance the asymmetry by making them negatives of one another here. And so we're constraining it in some sense because we're using this pairwise, we're forcing it to have this pairwise connection, whereas we're not doing that here, but we're adding, we're creating a scattering matrix with some extra asymmetry that this case might not have by forcing this behavior with each pair of RIS elements. In any case, you can see that the performance is very similar with a slight edge here in terms of the impact on the network. This set of curves here shows that the sum ergodic rate as a function of the number of base station antennas will not improve when the surface isn't present, whereas in fact, of course, it will improve when the surface is absent. This is for zero forcing. As the number of elements in the surface increases, the effectiveness of the attack increases. And as you increase the transmit power at the base station, you cannot overcome the attack. It basically, the average sum rate remains low, whereas of course, without the surface, it would continue to rise in a linear fashion. So number of base station antennas, amount of transmit power does not help you in overcoming this type of attack. And this slide here basically shows that if you know something about the CSI, of course, this is an idealized assumption, I understand, but if you did, for example, know what the line of sight the channels are, the line of sight channel between the line of sight component between the base station and the surface, and the line of sight components from the surface to the users, and you don't know the non-line of sight channel, but you do know their statistics, then you can optimize the connections and the phases in order to maximize the impact of the attack. So this dashed blue curve is the sum rate as a function of the number of base station antennas when there isn't a surface. Obviously, it grows. This is the performance you would get with a random surface that doesn't exploit any channel state information. And then the red curve is the performance you could achieve in this scenario where you did have this partial channel state information. Essentially, you would shut down the communications completely in that case. The black curves here shows the performance of some algorithms that don't require CSI, but that are tuned in a particular way that I won't talk about those, but that you can find in our paper. So these non-reciprocal surfaces with fairly simple design, simple, physically consistent design, can achieve a very strong impact, negative impact on the performance of a wireless communication link. But so a natural question might be, well, could you use such a surface in a positive way without implementing a TAC? And there are a couple of situations where you might envision such a non-reciprocal surface being useful. Let's take a case where we have a reflector array set up as a radar. So you have some source illuminating the surface. The surface is being tuned to transmit that pulse or that waveform in a direction that might reflect off a target. And if the reflection follows the same path as the illuminating waveform, a reciprocal surface would direct that energy right back to the transmitter. But if you have a non-reciprocal surface, you could direct that reflected energy to a physically separated receiver. And that would allow you some degree of isolation from the transmit waveform here. So basically, you're creating, in effect, a large-scale circulator. This is what a circulator does for a single pair of antenna, or for a single antenna. Here, you're doing it for an array by using this non-diagonal structure. Similarly, a similar type of application would create a wireless circulator, or say, for example, for a set of full duplex radios. So the radio in the middle has information it wants to send to this radio, which simultaneously is sending information to this radio, which is simultaneously sending information to this radio. In effect, creating, as I said, a wireless circulator that allows these radios to communicate with one another in this circular fashion without any additional interference caused by these transmissions. So I think that's basically it. I would say that we already know that these RIS, these reconfigurable surfaces offer a great potential for benefits to wireless systems. But as I've hopefully demonstrated today, they could potentially pose significant security risks. Channel reciprocity attacks being a key example. They're passive attacks, very difficult to detect. At least I think that last statement applies particularly to the non-reciprocal surfaces, because there's passive elements in the environment. You wouldn't really know they're there, except for the fact that your TDD communications are disrupted. No CSI is required, no synchronization is required, no precise models for the surface are required for the attack to be effective. We presented these two attacks: the disco approach, the non-diagonal approach, and I think there's some interesting avenues for further research, particularly how you might try and overcome this kind of non-reciprocal crack approach. The only ideas we've come up with so far essentially amount to doing things that you would have to do in an FDD system with a lot of feedback from the users, which negates the benefits of a TD type approach. And so this is still an open problem about how you might overcome these non-reciprocity attacks that are based on purely passive elements that don't change with time in the environment. All right, that's all I have, and I would be happy to entertain any questions.
Thank you very much, Professor, for the very interesting, clear talk on this unique application on non-diagonal RIS, malicious application. So are there any questions? Not in the chat for the moment. I can start. I can start maybe with the first question. When you mentioned assuming some CSI is available, you can some sort of optimize the surface. So do you assume that the permutation can be optimized on a channel realization basis or based on the statistical CSI?
So yes, in that particular example, we assumed that the configuration could be adjusted, but still with a pairwise constraint.
Okay. Okay.
But yes, you could in effect change which elements are grouped together, and also change in addition to the phases that are associated with those connections. Which, you know, I agree is an idealized assumption, but it does show that there's still a lot of gain to be had by trying to properly, or at least use some prior information to enhance the attack.
Yeah, yeah. So I guess with some switches in additional to the circulator, this can be achieved.
I'm sorry, I didn't hear your question.
I guess in addition to the circulator, do we need some switches to?
Yeah, if you wanted to, if you wanted to reconfigure, if you wanted to reconfigure the network instead of just putting it, instead of fixing the configuration and putting it in the environment, then yes, you'd need switches and other items like that, in order to implement it.
Yeah, and in the previous results, where there were the histogram plots, in the idealized case, how was it random, the permutation?
Yes.
Okay, just okay, yeah.
And then also in the pairwise case, the pairs that were chosen were random as well.
Okay, but constrained to be with that
The
constraint.
constraint have that phase relationship.
Yeah. So a question in the chat: which tool is used for performance analysis, MATLAB or any other tool?
Oh yeah, this is all MATLAB. I don't know how to use anything else. No, yeah, this is all done by MATLAB. The optimizations here were not, I mean, for example, with in the example where we tried to optimize the performance, this is this is an energy programming problem. It's very difficult. We use the genetic algorithm as the tool for doing it. Not necessarily the best, but that's another. I think it's a very interesting problem to be addressed here, because whether are you designing the circuit are you designing the surface by changing the impedances themselves, or are you just assuming this abstract model where you're adjusting the phases? That makes a big difference. Here we were assuming this pairwise connected case where you could adjust the phases. So the only thing we were actually controlling were the phases, rather than trying to choose the impedances that generate that behavior. That's a separate problem. But yeah, we haven't focused too much on the optimization problem yet.
Yeah, future direction.
Yeah.
So Arthur is asking, he say, thank you very much for the nice presentation. Are these attacks launched with non-reciprocal RIS stronger than those launched with conventional RIS or fully connected reciprocal RIS?
So it depends on what kind of attacks you're talking about. If you're talking about disco, which is the other type of attack where the RIS is changing in time, I would say that both methods are effective in disrupting the reciprocity of the channel. I wouldn't say one is better than the other. The only difference is basically the assumptions that underlie how they're implemented. But in terms of the actual degradation in the performance of the channel, I would say they're pretty similar. And but otherwise, I'm not quite sure what other attacks you prefer. The only ones that I think that are directly comparable are the ones that I've mentioned here, the disco approach compared to this other approach.
Yeah.
So there's another question: how would the attacker justify the usage of a non-diagonal over a conventional surface with the disco? So as I mentioned, the advantage of this non-diagonal surface would be the fact you don't have to change it. Its behavior doesn't change with time. You just put it in the environment and it acts like an environmental something in the environment that's non-reciprocal. And you don't have to be synchronized with the system, and a system can't exploit the fact that it's generating statistical variations in the channel that might be reciprocal. So those are the advantages of having this particular type of surface as opposed to the Disco approach.